Hi everyone. Today we will be talking about magnetic field due to current. So in the previous chapter we assumed that there is a magnetic field created by a certain source and we try to calculate the magnetic force. So today we will talk about one of the source of magnetic field, which is a current carrying wire. So this lecture is divided in two parts. The first part we'll talk about the magnetic field due to a current, circulating in wire, and we will deduce from that what is the force between two parallel wire or two parallel current. In the second part, we will talk about something called Ampere's law for magnetic field. That's what replaces what is Gauss's law for electric field. Okay, so let's get started. An electric current circulating in a wire, that's a source of magnetic field. So I would like to start my lecture by an experiment, to show you an experiment. And the first experiment that demonstrated that an electric current generated a magnetic field is this one. It was done by Ostrich. He was just doing a demonstration for his physics student, and it was about magnetic field and electricity. So he was running an experiment of an electrical circuit shown here, and there was nearby on the table there was a compass that showed magnetic field. Of course, a compass is naturally oriented toward the north. Okay, so and he saw that when he closed the switch, the current circulate and the needle start to move, to deviate from the north position. When he opened the switch, so there is no current circulating, the needle come back to the position, to the north position. He also did the following. He switched the battery, the terminal of the battery, so the current was circulating in opposite direction, and he found out that the needle is deviated toward the opposite direction too. So that was his first experiment that showed that indeed the current will generate a magnetic field. This magnetic field was felt by the compass, by the needle of this compass. Here we have a small animation of what is happening here. So when the switch is open like that, there is no current, and you see that when the switch is open, that the needle is in the north position. Again, the switch open, needle in the north position. When we close the switch, the needle is moving, and the needle is moved. Actually, the needle is aligned along a field line, along a magnetic field line. So the magnetic field line are in this direction, and it demonstrates that the magnetic field line are circle around the current carrying wire. So here we have a snapshot of one experiment. So in this experiment, we circulate a current in this wire, so the current is flowing in this direction, let's say. So that's a loop basically of current. And you see that the magnetic field line here, so basically here you have some iron powder, and the iron powder, they get the field, this magnetic field, and they orient themselves along a magnetic field line. So the magnetic field line, you can see here that they are a perfect circle circulating the wire. Here you have our spectacular experiment. So here we have a loop of current, and you see that magnetic field line are circulating both sides of this loop. Okay, and there is an interaction of the two fields here and so on. We know that is a magnetic field created by this current, but how to calculate it instead? So there is Biot-Savart Law that was attributed to the two French scientists, Jean-Baptiste Biot and Félix Savart. So basically, this law that what replaced Coulomb's law for electrical field. So in Coulomb's law, what we need point charge. What we mean by point charge? A particle that is charged, but the size of this particle is much smaller than the distance at which I want to calculate the field. So the same way in Biot-Savart Law, we need moving charge, right? So we need a current, but we need a tiny piece of current. So basically, if you have a wire here, you cannot apply directly this law. What we need here, we need a tiny wire. Tiny wire, this is L. Okay, that's the element length. That's the length of this red things here. As the magnetic field, C, B, and the strength of this field is given by a constant mu 0 over 4 pi. Mu 0, that's what we call permeability of a free space. So for electric field, we have a permittivity. For magnetic field, we have permeability of free space. So mu 0 over 4 pi, we have the current I circulating in the wire, and we have the element length dl, and we have something else. So you have a sine of theta and an r square. So let's start with r. What is r? The r is the distance between the element wire and the point at which I want to calculate the magnetic field. So that's r. And what is sine of theta? So what is the angle theta? The angle theta, well, it's the angle between r and dl. So this is the law that we call Biot-Savart Law, shown here in the color. And what is this permeability? Mu 0, that's 4 pi times 10 to the power minus 7 Tesla meter per ampere. That's the unit of permeability. So you will have this constant basically, mu 0 over 4 pi. What is it equal to? Just 10 to the power minus 7 in standard units. We know how to calculate the magnetic field strength, at least the tiny piece of it, dB. So you figure out if I want the magnetic field of the whole wire, I need to integrate this. But what about direction? How I can know the direction? So is into the board. The magnetic field is into the board, dB. Okay. So how you know that? Well, I will apply what I call a right-hand rule. So always there is a right-hand rule everywhere in magnetism, and this is a right-hand rule for current. What you do, you orient your thumb in the direction of current. So the thumb is oriented in direction of current. So let's say the current is downward here. You put your thumb in direction of current, and you see that your finger can curl or can rotate like that, and the rotation of your finger gives you the direction of the field. So here the field is into the page, and here the field will be out of the page. So if you take the opposite situation, you orient your thumb along the current direction, and you see that here your finger are pointing out of the page, and here your finger will be pointing into the page. Okay, so that's what gives you the direction of the magnetic field. If we have a wire here, we saw before at least an experiment that the magnetic field line are circulating the wire. So shown here basically. So the current here is into the page, and the field line are circulating the wire. So how we know the direction of the field line? Basically, you put your thumb in the direction of the current, so your thumb is into the page, and you see that your finger are rotating clockwise. Okay, so that's what gives me the direction of the magnetic field line. So how I know the magnetic field now? So at this point, for example, what is the magnetic field at this point? So you know the direction of magnetic field line. That's basically how your finger rotates. And we know that the magnetic field, what is it? Is tangent to the field line. So B is tangent. So if I call this distance capital R, that's distance between the wire and the point at which I want to calculate the field, well, the field will be given by mu 0 I, mu 0 is permeability, mu 0 times the current inside the wire, over 2 pi r is distance between the point and the wire, perpendicular distance between the point and the wire. That's for an infinitely long wire. So I have basically current circulating in this direction. So if I want the field at this point, for example, at this point, you see that first, if you do right hand rule or thumb rule, you will see that the field is into the page at this point. Okay, and if I call this distance r, so the field is given by mu 0 I over 2 pi r. The second situation is when we have a semi-infinite wire. That's an infinite wire, and I come at the end of this wire, at one end of this wire, and I want to calculate the magnetic field here, at this point, at distance capital R also. So the field basically is half of that, mu 0 I over 4 pi R. So how do you to go from here to here? Well, you multiply by half. Okay. How we can get this expression? So by integration. So we apply Biot-Savart law. So we have dB equal mu 0. So there is something missing here. That's mu 0 I forget the current here. Mu 0 I dl sine theta over 4 pi r square. What is dl? That's dl. That's dl. That's the element length. And basically I want to calculate the field at this point. So we know that the field is, we know direction of the field by right hand rule. So the field is into the board. And let's call this distance small r. Okay. Sorry, let's call this distance, sorry, capital R. Right. Small r, the distance between the element length and the point at which you want to calculate the magnetic field. And what is theta? Theta is the angle between the L and R. So it's this angle here. Since my wire is vertical, I can call this y-axis, it isn't? And I assume this is the origin of my y-axis, and this quantity here, this distance here, I will call it y, and dl basically is what? dy. I can replace it just with dy. That's the element length in the y direction, so I call it dy. So dB will be equal to what? Mu 0 I over 4 pi, that's constant, dy, sorry, sine theta over r squared. Now, when I move this element length, along a wire, what is changing? Well, the y is changing, the distance is changing, and the angle theta is changing. If I am here, for example, what is the angle theta? 90 degrees. Okay, if my dl is here, the angle theta is 90 degrees. So theta is changing, r is changing, y is changing. That's not good for integration. Integration, we need just one variable. So I express everything with a function of y. So what is r? R is square root r squared plus y squared. And what is sine of theta? We need the sine r over small r. Okay? So you plug this in this equation and you get dB equal mu 0 I over 4 pi, and we will have dy over, well, square plus y square to the power 3/2. That's basically small r cube. All this dB, they are in the same direction. Okay, all this dB field, they are in the same direction into the board here. So I can just add them. They are all in the same direction, so I will just add them up. So the field will be what? The integral of dB All these are constants, so that's the integral of dy over r squared plus y squared to power 3/2. So that's infinitely long, so y is varying from minus infinity to plus infinity. Okay, so you use calculus to calculate that, and calculus will tell you that. So by using calculus, you found out that b is equal to what? Nu 0 I r over 4 pi, just copy that. And this term, it will be equal to 2 over r squared. You cancel out things and you get here nu 0 I over 2 pi capital R. All right, so let's go to the next calculation. We'll be using also Biot-Savart Law. So here we have a circular arc. Take the situation in which I have a circular arc wire. Okay, the circular arc, it encloses a certain angle phi, and the center of the circle, that's C. What we will be calculating here, the magnetic field at the center. So how we will do that? By using Biot-Savart Law. I forget the I here also. So that's my Biot-Savart Law. What I will do, I will take an element length, dl, well, they wrote it here ds, is the distance, so is the position vector from the element wire to the center. These two vectors are perpendicular to each other because dl is tangent to a circle. Okay, an element length is always tangent to the radial direction. So theta is equal to 90 degrees, and a sine of 90 degrees, that's just 1. And what is r, by the way? Small r. What is it? Well, if I change the element length here, if I move the element length, the distance r is the same. What is r? That's actually the radius, capital R. So that's the radius. All right, so with this information, I can write dB equal nu 0 I dl sine theta is 1 over 4 pi, and we have capital R squared because that's a constant. So if I want to integrate this, along to get b, I need to integrate this. So what I need to integrate? I need to integrate just dl, element length. So I integrate the element length along the circular arc. What I will get? Well, I will get the length of this circular arc. And what is the length of a circular arc? What is that? So this will be equal to mu 0 I over 4 pi r squared. Okay? And what is the integral of dl? What is the length of this arc? That's just the radius times the angle, phi. That's the length of the circular arc. But phi expressed in radian. Okay? So if you do that, you will find that actually b is equal to what? Nu 0 I, is I missing here, phi over 4 pi r. R is the radius of the circle. Okay, so basically, if I write it properly here, b is equal to what? Nu 0 I phi over 4 pi r. Let's do this sample problem. We'll have this wire. And the wire, it has 3 parts. One straight part here, one curved part with an angle of 90 degrees, and another straight part. Okay. So this part I call them, this part of wire, the piece of wire, I call them just 1, 2, 3. And the question is, what is the magnetic field produced at the center of the circular arc? So we can write the following: B at C, that's B1 plus B2 plus B3. Okay? That's theorem of principle of superposition. That's principle of superposition. So let's calculate now B1. If I want to calculate B1, let's see now dB1. dB1, using Biot-Savart Law, that's mu 0 I, we have the same current here circulating, over 4 pi dl sine theta over r squared. So that's the straight part. We take an element length here, dl, shown, dl or ds, same thing. And what is r? Well, r is this. R is the distance from the element length to the point. That's r. What is the angle between r and dl? That's 0. So this is 0. What is sine of 0? Just 0. So dB1 is 0. It means the field is B1 is 0. Okay. Similarly, if you think about it, for the same reason, the magnetic field created by the wire 2 is also 0. So the magnetic field created at the center, that's just the magnetic field of a circular arc. Okay? All right. So, but that we just saw the expression before. B3, that's just mu 0 I phi over 4 pi r. What is phi? That's 90 degree, but be careful. We write phi here in radian. So what is 90 degree in radian? It's just pi over 2 over 4 pi r. And this will give you mu 0 I over 8 r. That's the magnitude of our net field at point C. What is missing here is the direction. Magnetic field is a vector, so we need the magnitude and we need the direction. The direction, we use a thumb rule or right-hand rule. So you put your thumb in direction of current, as shown here. You put your thumb in direction of current, and you see that your fingers are pointing into the board. So magnetic field is into the board here. Okay, that's the net magnetic field at the center. This is direction, and this is the magnitude. There's just something here. So we said that here we have a straight wire. So why we didn't use the formula mu 0 I over 2 pi r, just we described it before? Well, for many reasons. First of all, that's not an infinite wire. Nothing in the... And even if it was a semi-infinite wire, because it stopped here, even if it was semi-infinite wire, we cannot use that formula. Because that formula, what it tells us? Well, that formula, if you come back here, this formula, mu 0 I over 2 pi r, what is it about? It's about the magnetic field at a point at distance r from the wire, a perpendicular distance. It's not a formula for a point here in the same line of the wire. We cannot apply this formula. So in this example, the point is along the line of the wire. So that's why the field is 0. Okay. All right, so let's go to the next section, which is about force between wires.